Good afternoon, everyone. Are there any questions from the previous lecture? So in the previous lecture, one of the topics that we discussed was the IID assumption, and I thought to just share the Wikipedia page on the same, which is a very nice article. So the Wikipedia page also clearly mentions the identically distributed aspect of IID as well as independent, and they also nicely mathematically put this thing down. So let us assume that we have two random variables, capital X and capital Y, whose, in this case, they have shown the CDFs, capital Fx and capital Fy, but we could have equivalently have the PDFs. So the identical assumption says that the PDF is the same, right? The PDF evaluated or the CDF evaluated at the same input is the same. The independent assumption says that if you were to look at the joint probability or the probability of joint occurrence of two values x and y from these two capital X and capital Y random variable, you could factorize them as the PDF of the first one times the PDF of the second. Right. So this is a very nice article, and they also then mention in general for more than one random variable. So we'll quickly revise what we did last time before going ahead. We said that because of the IID assumption, we can nicely factorize and draw graphical models such as the following. In this case, we are having some data which is distributed normally with a mean mu and variance and a scale sigma. So we can have this kind of a graphical model where we have mu and sigma are the input parameters to the normal distribution object, and from that we are drawing these samples x1 through xn. Importantly, x1, there is no arrow between x1 and any of the other x's, which is signifying the independence, and the identical assumption is coming from the fact that for each of the value, each of the draw that you have from this distribution, you have the same parameters mu and sigma, or we have the same identical distribution. We could have also put a plate around this zone around this variable xn to show that we have n repetitions. And because of this, we wrote that the factorization of the likelihood, where the likelihood is the probability of data given theta, we can now write it as x1 given theta, x2 given theta multiplied by xn given theta. Right. So while it's a simple result, we're repeating it many times so that we are able to get a good grasp of this. We then discussed, we wanted to understand about MLE. So we took this small quiz where we had 3 classes, where we had different distributions. The marks in these courses were distributed normally with different means and sigmas. And we said that if we randomly picked up a student and said that the marks were 82, we had to guess most likely whether they were from C1, C2 or C3. And we discussed the procedure for doing that. It is to firstly draw the PDFs. Right? We have the PDFs for the 3 classes C1, C2, C3. You now look at the observation which you have, which in our case is 82. You draw a vertical line at 82, and then you compare the probabilities. Right? This is a simple case because we have a single observation. If you have multiple observations, what is the change we need to do in this figure? So in this figure, we have a single student, 82 marks. If we had 2 students, 82 and let's say 60, what change do we need to do? For each observation, we draw a vertical line, we obtain the probabilities, and what do we do with the individual probabilities? Multiply them, because that's the factorization which we saw. So this is where we stopped last time. We want to calculate the maximum likelihood estimate for the parameters of the normal distribution. Right? So we'll first note down the probability density function of a univariate normal distribution. So we have a univariate one, which means there's a single value which you are looking at, not a scalar, not a vector. Given as a function of mu and sigma, the density is as follows, which you already know, 1 upon root 2 pi sigma square e to the power minus x minus mu whole square by 2 sigma square. Again, we'll assume that we have a data set. We have sampled from this distribution. We have got certain set of observations, x1 through xn. We'll again make use of the IID assumption. So what we want to do is to estimate the parameters theta equal to mu comma sigma from this observed data, from the observed endpoints, right. So, now this is more in the ML framework of things. We are given a data set and your task is to estimate a certain set of parameters which best describe the data set. We have discussed that the definition of best describe the data set is using the likelihood function. So, in this case we write down the likelihood function as probability of data given theta, which is probability of di given theta. Just because of the IID assumption we can break this down, and we write it as a function L of mu comma sigma square. Right. So, we typically use the letter L here to denote the likelihood. Right. Importantly, the function L is a function of what variables? Mu and sigma, assuming the data is already given to you as a constant. Right. So, it is a product of the individual density terms evaluated at each of the xi's. Right. This is not different from what we discussed a few minutes back. If you are given a single observation, you can evaluate f of xi at xi equal to 82 for the 3 normal distributions, and you will get this certain probabilities. But if you had multiple observations, you will have to multiply each of those probabilities. So, now I am going to just expand this out and write this as I am taking the log of it. Can again someone remind us why are we taking the log of the likelihood function? One at a time. Okay. Addition makes process easier for calculation. Any other point? Sorry? Numerical stability is another reason. And the reason why we can take the log transform is because log is a monotonically increasing function. Right. So, we take the log of the likelihood. Now, we convert the multiplication to summation over the n data examples, and another advantage we get with the log, especially in normal like distributions, is that you have an exponential term. So, log and exponential will play nicely and you will get certain things in linear way. So, log of likelihood turns out to be log of this big term. So, log of a into b is log a into log b. That is the log of a into b is log a plus log b. That is how we break this first term, and then log of this exponential we can just directly write as minus xi minus mu whole square upon 2 sigma square. And if we do a bit of adjustment, we can write this as minus n over 2 log base 2 pi minus n log sigma minus 1 minus 2 sigma square xi minus mu the whole square. Right. So, it is a big looking expression. You have a constant term. Constant means constant in terms of it does not depend on mu and sigma. The second term depends only on sigma, and the third term depends on both mu and sigma. Right. So, this is one way in which we can calculate the log likelihood given some data, but I will show you a programmatic way to do the same without having to write this sophisticated looking expression. So, before that, let us also look at a simpler example. So, I have assumed that I have been given some data, right. So, I have been given some data, and if I want to look at how the likelihood and log likelihood are behaving. So, this is again showing you that you should be using the log likelihood wherever possible instead of the likelihood term, because the likelihood becomes 0 at most of these places, whereas the log likelihood is not 0, and this 20 is one observation, a single observation that I have, right, from a normal 0 comma 1 I think, right. So, you have a normal 0 comma 1 which generated the data. From that you are trying to observe the value 20, you are trying to look at the likelihood of generating that. So, the likelihood in terms of probabilities, because the numerical precision is 0, but the log likelihood is nevertheless a term. So, which I again mentioned, you draw the likelihood, you draw the PDF and you draw the log PDF, you take the observation, you draw a vertical line and see where it cuts. It cuts the log likelihood curve at minus 10.1639, right. Now, if you were to calculate log likelihood for more than one example, let us take a look at this. Right. So, we have 5 examples, 5 samples being drawn from a normal 0 1 distribution, and if you look at these samples, they turn out to be between minus 1.2 and 1.04. If I were to draw a scatter plot around them, they may look like the following, quite spread across. There are only 5 examples. Now, this is the main function I want you to look at. So, I am trying to calculate the log likelihood of a given set of samples. I have just made, for some specific reasons, I have made this function simple and I have not added samples as an argument to this function. So, I have mu and sigma and I am just converting them to torch tensors. Again, there are some specific conveniences I used. I create, for a given mu and sigma, I create a distribution object, normal distribution object. I evaluate the log probability over all the samples, right. This is happening in a, this happens in a vectorized way. So, to understand this better, we can write, so we can create torch dot distributions dot normal 0 1 and this dot log prob of samples. If you were to do this for each of the sample, right, you had these samples 0.3. So, which of them do you think will have the highest log probability? First, let us see if you have that understanding. Minus 0.22, because that is closest to the mean, which is 0. So, let us see if indeed that is the case. Indeed, the log probability for the second sample is indeed the highest, right. So, this is giving us the log probabilities. So, log PDF at sample 1, log PDF sample 2, log PDF sample 3, so on and so forth, and now we can sum them up, right. So, in the formula also we had written the log likelihood is the sum of the log PDFs evaluated at individual data points, right. That is essentially what we have done in the function. We take a distribution object, we find out the sum over all the samples log prob. In this case, I am just returning this same thing. Right. So, this is in fact for this specific example, I had plot normal 0 comma 2. So, I have a normal distribution. So, if mu is equal to 0 and sigma equal to 1, then, and if this is the log PDF curve that I will get over the space of minus 5 to 5, and I have 5 observations going from minus 1.2 to 1 point something, draw vertical lines, mark their values, sum them up, right. So, this is the graphical way of understanding the same thing which we had written in code. You find out the log probability over samples, sum them up. And interestingly, this also gives you the power of now varying the parameters. So, at sigma equal to 5.05, the log likelihood turns out to be minus 12.7. Which direction do you think I should move the sigma pointer, sigma slider to improve the log likelihood, to increase the log likelihood? Should I decrease it? Should I increase it? Decrease. Why? Because the true value was, from which the data was generated, was 1, right. The data is generated from mu equal to 0, sigma equal to 1 normal distribution. So, if I reduce the sigma, you will notice that the log likelihood expression, it is increasing, it is going to minus 10.08, further increases, it goes to now about minus 6, it increases further. Why is this happening? We had generated the data from 0 1 normal distribution, but it turns out that at mu equal to 0, sigma equal to 1, our log likelihood is lower compared to using mu equal to 0, sigma equal to 0.9. Why do you think that is happening? So, no, so my question is actually simpler. The true distribution which generated the data was normal with mu 0, sigma 1. I took some samples from it. Now, I am trying to see for what value of mu and sigma is my log likelihood or the likelihood maximized. It turns out that my log likelihood is higher for mu 0, sigma 0.9 instead of mu 0, sigma 1. Why do you think that is happening?
Exactly the same distribution like the sample.
We would need more samples.
Good. So, if we had a lot of samples, then our observation would have been correct. But since we have a small number of samples, we cannot make such claims here. Right? So, if you, in fact, here it seems to be something like 0.8 or something between 0.8 and 0.9, value of sigma is the best. But at the same time, we forgot about mu. So, maybe we need to adjust mu a little bit. So, in fact, this seems to be the best thus far. Mu is minus 0.1, sigma is 0.8, right. So, what am I trying to do through this exercise apart from showing that widgets are cool?
So there is a bias in taking sample.
Okay, there is a small amount of bias which exists. The sample is a small one. So, therefore, we are not able to recover the exact parameters, that is one. What else are we doing? So, what is the procedure that I am doing is called? What do you think that is called? We are trying to estimate two parameters, but in which way? So, what am I doing when I move the pointer, when I move the slider? What do you think I am? Grid search, right. So, I have a grid, I have a 2D grid, I am varying mu, I am varying sigma, right. So, you could have thought of writing this in a nested for loop, right, and then you would have got the full 2D grid, right. And then you are trying to figure out amongst these chosen set of points along the grid, which of them is the best, right. So, for very small grid spaces, this is a good enough idea. But if you have bigger search spaces, what is the procedure we typically use to estimate some set of parameters? Some optimization method like gradient descent. But before that, so this was looking at it when we had two sliders. Now, let us look at this from a different perspective. If we were to write, so let us now look at a few possible values of mu's and sigmas, right. And as I mentioned, we will just write a for loop, nested for loop. So, I want the log likelihood as a function of some mu and some sigma, right. Essentially the same as what we have done over here, but I want it in a 2D grid instead of having to move around these pointers. So, essentially what I do is I can create a bunch of mu's, the mu values where I want to evaluate my log PDF, that is from -1 to 1 with spaces with 100 spaces between them, 100 values between them, and similarly sigmas goes from 0.1 to 1.5. Why have I chosen this values of sigma and not something similar to mu's? The mu's from -1 to 1. Why does sigma have a different set of values that I have given? Sigma can't be negative, right? It is the standard deviation. So, you have to start from something non-negative and you have to go to something more positive. If you understand this specific point, one of the questions in the assignment will make a lot more sense to you. Why are we using log scale instead of scale over the optimization? So, this is the answer to that question. Not the full answer, but this is, if you know this, you will almost got the answer now. And if I view this, and so at this point I will get some matrix, 2D matrix, LLS, I just called it LLS, it's a poor name, and I can take a NumPy object around this and create a data frame to show you what exactly this is, right. So, you have mu's along one of the axis and you have sigmas along the other axis, right, and then you get this 2D grid. Now, in this 2D grid I am trying to figure out which value of mu and sigma will give me the minima, right. So, this is through a grid search procedure. If you wanted to make this fancy, you would write index equal to mu's dot numpy and columns equal to sigma dot NumPy I don't want to plot. I don't know if this is only for you or if this is only for me or for you also. Copilot has become bad for the past few days. So perhaps they're just running through different iterations. So this is how the data frame might look like for this value of sigma, and these are the values of mu's, and then you're trying to figure out the best amongst them. Or we could do a much more visual understanding of the same. We could create these contour plots. So this is how a contour plot might look like. So I've also plotted, so let me actually increase the data set size to 50. Otherwise it's a really small sample. Right, so for this data set size, I've marked these contours. Does everyone here understand what contours are? Right, or how they are derived from surface plots? If you have surfaces, ridges surfaces, you're trying to view from the top. And I've purposefully also written down the levels. So this level minus 340.92 means if you follow along this locus, if you follow along this path, the log likelihood along all of these paths is minus 340.92. So it's clear that going centered is going to reduce the log likelihood, is going to increase the log likelihood, maximize the log likelihood. And at this point, I get the maximum log likelihood, which is about minus 72.79. Right? So this is the typical plot you may get. Of course, you may, like I purposefully spent enough time on this so that I can mark these things and I can show you the contour levels. It does take a bit of time, but I think it's worth the effort. You get more clarity this way. But this is still very confusing because you're not able to see any level sets. So that's happening because your ranges are very wide at this point. If you had a smaller set of ranges, or before that, I had the samples. My samples.mean is minus 0.0623 and my samples.std with correction equal to 0 is 0.7523. And if you notice this carefully, on sigma axis I am roughly around 0.7523 and on this I don't seem to be, okay, I have not run this code, that's why, right. Okay, there seems to be some disparity in the results that I've got now. I hope I have not redefined samples anywhere. Let's just take these. So like students say that that I promised that the code was working, I am similarly saying this code was working, giving me perfect results just a few minutes before the presentation. And it's giving me samples.mean is minus 0.088, 0.0089 and the samples.std is this. Let's first run the other one where I'm defining this again. Okay, the code has definitely broken. The maximum likelihood has gone to some weird place. Let me actually see if I have the stored version of this to prove my innocence that I had indeed done this correctly. Yes, I had indeed done this correctly. So if you look at this point, this seems to be, so if you, in this particular plot, I've restricted the axis a little bit for mu and for sigma. And now you can see the contours and you can see that this particular point has a likelihood, log likelihood of minus 5.67. So in a typical problem setup, you'll be given the data set. you'd be computing this log likelihood function as a function of mu and sigma, and then you let gradient descent figure out, work through these contours and try and reach to this minima. Right. So, even though you could have used gradient descent directly, but I still always suggest to draw figures like this, including making the contours lines. So, one of the reasons is you want to understand how much important is one particular parameter. Right. So, in this case, both the parameters seem to be reasonably important, but in many cases you can have that all of the variation exists only along one parameter. There is not enough variation along the other parameter. So, you can then restrict the space for one of the parameter and look at a larger space for the other parameter. So, this is some quick experiment I will always suggest you to do. Importantly, if you go back to the code, now if you have to write a gradient descent loop around this, you can start with something like this, a function which accepts a mu and a sigma, right, and it returns the log likelihood. You do not need to return the distribution, which is a scalar in this case, right. Accept two inputs, give a scalar, optimize over mu and sigma. So, you do mu equal to mu minus del of this, the gradient of this with respect to mu and with gradient with respect to sigma, and you are done. So, at this point it should not take you more than 5-10 minutes to be able to code. Once you have a basic version of gradient descent working in Torch, you can pretty much use this function. Any questions till now? Okay. So, this is a log likelihood function. You could have, I think this will be good exercise for you to try out. You can directly write this formula also, write this in Python and see if you get the same log likelihood as the one which I have got using Torch distributions. You should. Right. Okay. At this point, let's do a bit of exercise in your notebooks. You start with this function. It's a function of mu and sigma. Find the derivative with respect to mu, set it to 0 and find out the maximum likelihood estimate for mu from this data. Right. So, that is the goal. Given the log likelihood, which is a function of mu and sigma square, can you find out the derivative with respect to mu and set it to 0 and find out the most optimum value of mu or the maximum likelihood estimate value of mu. You should know the answer, which we have already shown. It should turn out to be the mean of the data. Can someone ask the classroom support if they can turn on the ACs? They promised a few minutes back. Is the AC working in the back? Can someone ask? The important thing is to first consider that there is only one term which has mu. So, the partial with respect to the other terms is just 0, and in the other term, in the only term which you have mu, you can assume sigma to be known or constant. So, therefore, it is a very simple function of mu.
Sir, but can sigma should be a function of mu also?
Sigma should be, why should sigma be a function of mu?
Because sigma means summation of observations minus mu and whole squared.
Okay. So, what Ritik is saying is that sigma, you can think of some relationship between sigma and mu. So, there is indeed a relationship between them, and you have to constrain them by the degrees of freedom that you have. But if you really want to go down that route, it's a 2-page mathematical derivation which relates both these terms and describes why through this procedure the sigma that we obtain is a biased estimate. So, I do not really want to go down that full route. I will go that route partly, where we will understand why exactly what you are saying causes some problem, causes some underestimation of one quantity. For now, let's assume that the procedure is find out mu first and then find out sigma. Okay, what is the value of mu MLE that we obtain? Just the mean of the data. So the only term containing mu is the last one, and we just need to find out the derivative with respect to that. Set it to 0. So 2 times summation I equal to 1 to n xi minus mu equal to 0. Therefore, mu hat MLE equal to 1 over n summation xi, right, which is quite intuitive. If you're given some normally distributed data, you take the mean of those observations. That will be most likely the best estimate for mu of the data. Yes.
Similarly, will the best estimate for sigma be the standard deviation of the data?
Next exercise. Can you figure out the maximum likelihood estimate for sigma square? So now you have to consider this function, the log likelihood function. It's a function of mu and sigma square. Now there are various ways to solve this. One simple way is to find out the derivative of this with respect to sigma and set it to 0. You could have found it with respect to sigma square, etc. For now, let's consider the derivative, the partial with respect to sigma, set it to 0, get some value of sigma MLE. But as Ritik was again asking the question, so when you do this derivative and set it to 0, you will need some value of mu, right? And that value of mu that you will get, you will want to put is mu MLE. So therefore, you are constraining the sigma based on the mu MLE that you obtain. Okay, so if I find the derivative with respect to sigma, or the partial with respect to sigma, I have this minus L log sigma term whose derivative, whose partial comes out to be minus n over sigma, and then I have a term of minus 1 over 2 sigma squared. So for this way I get sigma cube term in the denominator. So it will be something like this. So it will be minus, I multiply throughout by sigma cube and both sides. I will get sigma square MLE equal to 1 minus n, I equal to 1 to n xi minus mu the whole square. So this mu that we use is mu MLE. So this estimate of sigma does indeed incorporate the mu estimate that you obtain, right? So therefore, you have to go in this sequential fashion in order to obtain this sigma square, which itself is causing some trouble. Right? Does everyone follow this? If you just work it out, you should be able to solve this. Otherwise, the slides are for your reference. Let's try and understand that why this particular estimate is not a very good estimate, or there is some correction needed to this. So if you notice, I had written some code. Samples.mean, samples.std, correction equal to 0. Right? Have you ever used this kind of a term whenever you're finding STD, standard deviation? Let's perhaps take another example. Not start with this. We have taken some data. So data is some 100 odd samples taken from a torch distribution. So let me convert this to NumPy and do NumPy dot standard deviation. This turns out to be 1.08 some value. Let me do PD dot series of data dot NumPy dot standard deviation, some different value. Right. So this is a question I asked in the first slide also, in the first lecture also. Turns out to be different value. Right. Now let's continue this. Now we have two approaches giving us the value 1.0862. This has been rounded off till 4 decimal places. One of them giving 1.0807, which is correct. Majority wins.
Both are correct.
Okay, let's do something else. Let's look at the documentation for toward standard deviation. It says calculates the standard deviation over the dimensions specified by something something, and it mentions correction equal to 1. Right, so this is the same correction term which I was using, and this correction is the Bessel's correction, and there seems to be a good Wikipedia article to it. In statistics, Bessel's correction is the use of n minus 1 instead of n in the formula for sample variance and sample standard deviation. Right. So then perhaps what is happening is that some of the implementations are dividing by n, and some of the implementations are dividing by n minus 1 to calculate the sample variance. Right. And if we go back to the code, we can write another version of this, torch.std of data with correction equal to 0. Okay. So can you now see that the NumPy standard deviation formula is the same as torch.standard deviation with correction equal to 0, right? So both of these are the same formula, and now we can see why these formulas are needed and what exactly we have when we mean by n minus 1 used to divide or n used to divide the standard deviation. So if you go back to the slides, so what I am saying here is that sigma square MLE is the sample variance, right, divided by this n term, right. Instead we divided this by n minus 1, we will get a slightly different formula which some of the implementations are using. Okay, before I ask that, let's try and hear from the audience that why might you be dividing by n minus 1 instead of n? Why do you think that may make sense? If you know the answer, I don't want you to say the answer, I want you to be thinking fresh for this. The important thing in the Wikipedia article was that this is sample variance. The word sample is important. Okay. Any thoughts? If instead of dividing by n, I divide by n minus 1, what am I doing? You'll be increasing the variance, right? So what we're trying to say is that the maximum likelihood estimate for sigma square which we obtain is somehow not accounting for the full variance. Does that give you a hint? Yes.
Maybe increasing variance is done to compensate for the fact that the sample may not represent the entire movie.
Excellent. Excellent. So that's the perfect answer. The sample may not be able to represent the entire variance. Therefore, we need some correction factor to account for more variance. Let's take a look at that. We'll be looking at population versus sample. If it doesn't get clarified, you can ask again. So we have the population. Let's assume that we have a population which is distributed with the mean, mu and sigma square through a normal distribution. We know this for now. This is the perfect distribution which generated the data. Now, generally we will not be given the distribution, but we will be given the population or the sample from it. Let's assume that the population is infinite number of samples from normal distribution with the same normal distribution. Now, we will never have infinite samples, but let's assume that this is as close as possible you get to infinity. These are the infinite samples that I have drawn from this distribution. This is the entire population. Now, we will generally always be given a sample from the population, right. So, if we were to do a voter count and we want to do some exit polls, we will be picking up a sample from the entire population, right. So, typically we want to be estimating quantities given a sample and not the entire population. Given the entire population, it is very cumbersome, right. Similarly, in machine learning, you have to fit a neural network of, let's say, trying to predict the electricity consumption of the campus. Infinite samples would mean that you have infinite amount of data. Every millisecond you are collecting the data, right? But that's not feasible. So you will typically be given a finite number of samples. And then a goal becomes to estimate the parameters mu and sigma square from some set of samples or some sample that is given to you. Right? In this case, let's assume that we could have had two such samples of size 10. Right? One is the red set of samples, the other is the bluish set of samples. You could have picked up any such 10 samples from this distribution. And that's where the answer lies. Let's pick up, so we have the same ground truth distribution of mu 0, sigma square 1. Now let's pick up a sample size 3 from this distribution. I have 3 crosses to denote 3 samples that I picked. Now in each of the slide, I try and fit a normal distribution to the 3 set of points, to the number of samples that I have. Right? In this case, I have only got 3 samples. I fit a normal distribution to it. And naturally, it seems that the mean from the samples is not 0, right? It's slightly greater than 0. And the standard deviation from the samples is 0.38. So the standard deviation, if you notice, is lesser than the standard deviation which you might have seen if you saw the whole samples, the whole population. Right? But do you think, is it possible that, so thus far I'm making this claim that, and Ritik also answered this, it seems feasible to us that if we take a sample, we would be always underestimating the variance. Does everyone agree? Anyone who disagrees? You get a +1 if you say the right answer. Okay, I'll.
No, I agree.
Okay. So if we have this set of examples, what is the variance? Is it 1, greater than 1, less than 1? Greater than 1, right? So therefore, the intuition might break, but if we look over a larger number of samples, this will, just give me 1 second. So we take 3 samples. In this case, because the 3 samples just turn out to be very far spread, and because we have only got 3 numbers, so therefore the variance will turn out to be much larger than 1. Right? If I take another 3 set of samples, mu is again not 0, so it's pretty much skewed to the other side, and sigma square is almost close to 0. There is no variance in these set of samples. Let me take another 3 samples. Another 3 samples, another 3 samples. Now this is an important plot inspired from a very wonderful set of videos from Khan Academy. So if you notice, I have drawn these red dots, right? So what I did was I collected 100 such samples of size 3, right? 100 such data sets of size 3. For each of this data set of size 3, I calculated the mu and the sigma, right? So I have 100 such data sets. Each point is representing a data set of size 3. I found the mu hat and the sigma hat, right? So like this is one such data set whose mu hat is 0.06 and sigma hat is 0.12. So it may like somewhere around here, right? This is one such dot. I obtained 100 such dots. Now, if I take the mean of the mu's which I had obtained, right, I take the mean of all the mu's which I had obtained across the data sets, that is almost 0, right. Whereas, if I take the expectation of the sigma square which I had obtained across the different data sets, that turns out to be 0.65, right. So, what do we conclude from this? Given a data set, given 100 possible data sets of size 3, if I were to calculate mu for each of them, or I were to use MLE to find the estimates for mu and sigma for each of them, and if I were to take an expectation over them, I'd be able to recover the population mean correctly. Whereas the variance of the population, am I able to recover? I'm underestimating it, right? I'm underestimating by quite a big factor, 0.65:1, right? Let's repeat this procedure. Sample size 4, what do you think will happen once I move from sample size 3 to 4? What will happen?
The mean will get closer to 0.
The mean, okay,
Also, the sigma square will go closer to 1.
okay, any other answer?
Sir, as per the mean will obey the CLT, which means that the mean values, the observations of mean will be even closer to 0,
Mhm.
even though the expectation of them might not change more. And the sigma square which we observe will be a more accurate representation of the actual, like it will be closer to 1.
Okay, good, good. So in this case, for sample size 3, if you're just looking at the x-axis, can you see that there is a lot of spread, right? What do we indicate by that spread? Now we're getting into slightly technical stuff. If you're not careful, you may miss that.
That is because the Gaussian will spread.
No, no. So what do I mean by this spread? It's the variance in my estimation of mu, right? That seems to be large, even though my bias is 0, right? So let me first go to one slide which shows the definition of bias. So we're given an estimator theta hat for the true parameter theta. I can calculate the bias as the expected value of that estimator minus the true value, right? In this case, the example that I'm presenting, what am I calculating the expectation over? The different data sets, right? So theta means theta is replaced by mu or sigma, but what is the expectation calculated over? Like what is the source of randomness? That is what my question is. The different data sets, right? So over the different data sets, we can calculate the mu hat and take an expectation over them and see how different it is from the true value, right? That is the expectation. If we do the same thing for sample size equal to 4, you'll notice that again we have some mu hat, some sigma square hat. I'll directly go to the main plot. What do you notice? The expected value of mu hat is still fairly good, right? Very close to 0. The expected value of sigma square hat is now much better. It's closer to 1, which was the true value, right? Let me do the same for sample size equal to 5. What do you now observe? The expected value of sigma square is getting better. It's getting closer to 1, where the expected value of mu hat is largely remaining unchanged. Another thing you could do is to now also carefully look at the x-axis spread for mu hat and see if we can see the decrease in variance or not. We have a lot of samples between minus 0.75 and 0.75 for sample size equal to 5. If we had sample size equal to 4, let's see if we sample size equal to 4, we can see that we have a lot of points outside of -1 and outside of +1 also. So there seems to be larger variance in our estimates of mu hat. And for sample size equal to 3, even larger variance in the mu's which we could have obtained. Sample size equal to 5, sample size equal to 10. Okay. Now if you look at the variance across the x-axis for the values of mu, between -0.5 and 0.5, you can have majority of the samples now, right? Which means that the variance in our estimation of mu hat is reducing. Our estimation of mu hat was already unbiased, almost unbiased. Our estimation for sigma square is getting close to the true value, right? At sample size equal to 100, now the variance in the mu hat estimates is fairly small. our expected value of sigma square hat is almost 1 now, right, but still not 1. Let's make a data driven plot and see if we can come up with something to improve this plot. I've forgotten about mu's for now. I'm only looking at sigma squares. So my estimated standard deviation is shown on the y-axis and my sample size is shown on the x-axis. So as we increase the sample size, it seems we're getting closer to the true value, which was 1, right? Now can you tell me a transformation of these numbers, right, so that I can get the true number, which is 1? Can you think of that? Okay, let everyone think. Let me repeat the question. For x, for sample size equal to 3, I get the value 0.65. Can I multiply this with some number, with some corrective factor, or I add some corrective factor so that I get 1? Similarly, for sample size equal to 4, can I divide, multiply, add some corrective factor so that I almost get 1? Any thoughts? Yes. Okay, good. So you're telling that it has to be a function of n, true. Are you proposing an additive function or a multiplicative function? Multiplicative, okay, good. So let's multiply all of these previous numbers with n into n minus 1, right? So 0.654 into 3 over 2 into 1.5, 3 over 2, it almost gets us to 1. 0.76 into 4 over 3, 0.76 into 5 over 4, 0.976 into 100 over 99. Right? If you do this, the revised estimated or the corrected standard deviation which we'll get is now almost close to 1, right? A far better estimate. So we had to do a corrective multiplicative factor, which was n into n minus 1. Right? So we have shown this empirically that this seems to be a good result, and this is exactly the correction factor which is mentioned in the, which is known as the Bessel's correction factor, which was mentioned in the Wikipedia article. Right? So essentially, what we are saying is that the MLE estimate for mu is correct, is unbiased, but the MLE estimate for sigma square that we obtain is a biased estimate. It undercounts the variance. In order to increase the variance, sample variance, and correct it to match the true variance, we will have to divide by n minus 1 instead of dividing by n. Right? And the other thing which we can also realize from this is, as the sample size n increases, this corrective factor becomes irrelevant, because n into n minus 1 is almost 1 for a large value of n. So this brings us back to the bias of an estimator. So this is the definition which we had previously also seen in the machine learning course. We're trying to estimate a quantity theta hat, where the true quantity is theta, and this is just the expectation of theta hat minus theta. Right? And it's supposed to be unbiased if the bias of theta hat is 0, and it's supposed to be biased if this function turns out to be a non-zero value. There's a bit of maths we can show. Easy enough maths to show that we can come up with this derivation also using a bit of maths and expectations. But before that, I want to go back to bias variance as we had studied in the ML course, so that we can tie up these two concepts, right? These are the set of slides which we've seen previously in the machine learning course. We'd said that we had some true function f true, which is some function like this. We have a noisy observations because we're never able to observe the phenomena properly, or the process is inherently noisy. So we never get f true of xi, we always get yi, or we always get observations which is the true function plus noise, right? So what is the true function value which we are trying to estimate? What is the true function which you're trying to estimate? F true. As simple as that. So essentially in machine learning, we are trying to obtain some estimate of the true function. That should always be our goal, right? We want to get as good as possible an estimate of the true function, right? So our goal is to get some f hat which is very close to f true, right? Let's consider a very simple function, a decision tree of depth 1. Now, again, we could have been given the entire population, but we are never given the entire population. We are always given a sample from the population. Let's say we are given a sample data set 1 from the population. So, if you look at the leftmost plot, left top, if we are learning a decision tree depth 1, we learn a straight line, right? So, we would have learned f1 function. Similarly, given a slightly different data set, we might have learned a f2 function. Slightly different data sets, we would have learned a f3 data set. F3 function, right? So none of these functions seems to be matching the true function, right, which was like a quadratic function. But this is the other way to look at this. We have now multiple of these models of functions, and I can obtain an average. Data set. I can obtain an average estimated function through this, which I'll call my f bar, right? And I am calculating the expectation over the different functions which I could have learned from the different data sets that I could have been given, right? Exactly same as what I'm doing in the whether to figure out whether mu and sigma are biased or unbiased. So I look at my f hat, which is my average function, and I have my true function, right, which is f true. Can I now find out the difference between f bar and f true to tell the bias in my model, right? We are using the exact same definition in today's class as we had seen in the previous ML class, just that today we have looked at it more mathematically, more fundamentally. So this is denoting the bias. How well am I able to match the true function, right, or the true value of interest? In today's class, the true value of interest is mu and sigma coming from the population. In this class, it was the true function which generated the data, right? So this is indicating the bias that we have, which is the deviation of a model from the true function. What about the variance? So this is just indicating the variance. So if we had multiple different functions which we could have learned, we look at the variance across those functions, right? So ideally we want an estimator which is unbiased and has low variance, but we typically never get that. We typically have some bias variance trade-off. Bias means that on average I am able to get the true parameter or not. Variance means that how much variance do I have amongst the different estimators that I could have obtained, right? Questions? So even if you're not able to get some part of this course, of this lecture, I would want you to go back to these set of slides, right, and think about just repeating this experiment over time, right? Just write some code for this. You shall get a better understanding of what we're trying to do over this experiment. So another thing which we discussed in the previous lecture, in the previous course, was with regards to SGD, stochastic gradient descent. Is SGD a biased estimator or an unbiased estimator? It is an unbiased estimator. But what are we trying to estimate? The true gradient, right? So if I go back to slides. Right, so in gradient descent, in match gradient descent, we are given some loss as a function of the sum of the individual losses over the n data points, and we want to find out the gradient with respect to that. If we are given the entire data set, this is the gradient that we will obtain. Stochastic gradient descent, we have a single data point. over which we want to compute the gradient, right? For a single data point, some x and y, you compute the gradient, but that gradient is an estimate of the true gradient. So, I will just call that delta L hat. But if you were to take an expectation over delta L hat over all the sample points, n sample points, that turns out to be delta L, right. So, the expected value of your estimator is the same as the true value. Therefore, this system has no bias, this estimate has no bias, right. So, all of these things we are just discussing to show that MLE can be biased, right. That is the large, that is the main crux that I want you to think forward, take it forward from this class, that MLE can be a biased estimator. Some cases we can very simply apply some correction factors as we have done. Questions? So, I am leaving you with a reference which we can use. It is a very nice course website from Penn State, where we are discussing the unbiased estimation for different kinds of different random variables, including the one with of which we are discussing, normal distributed random variables, and there is a bit of small bit of derivation. The derivation for sigma square being biased is a little bit more involved, but the steps are there. Okay, any questions? Everyone tired? Okay, let us do some simple distribution now, for which we have already seen the main result. Yes.
How is using Bessel's correction factor decreasing the bias?
Decreasing the bias. So, the Bessel's correction factor is going to give you the true variance. I mean, it's giving you it's taking you as close as possible to the true variance, because if you look at this derivation, so if you follow this derivation, you will figure out that the unbiased estimator for sigma hat star is n minus 1 over n. So, you can prove it mathematically also.
But we were talking about bias in estimating mu.
Just one second. Sorry. So, unfortunately, many things are like, I was getting an OTP and my father was trying to contact me, sorry, and he was trying to call me since a long time. Yes.
Sir, are we, sir, we were talking about decreasing the bias in mu or sigma?
Mu is unbiased. The estimate for mu is unbiased. The estimate for sigma is biased. You are trying to reduce that bias. So, the bias is towards underestimating. So, therefore, you are trying to increase your estimate for sigma square by using this correction factor of n into n minus 1. So, you can look at all this maths and get bored with it, or you can just look at these visuals and mainly try and understand that whenever you are given a sample, there is a high possibility that you may underestimate the variance, right? Whereas for mu, that is not the case. Let us go back to MLE for the Bernoulli distribution. So, we have seen let me go back and discuss the Bernoulli distribution now. So, the Bernoulli distribution we have seen earlier in the previous course again. The PDF is given by p to the power x into 1 minus p to the power minus x, where x can be either 0 or 1, denoting a heads or a tails, or a success, a failure or a success. P indicates the probability of success, right? It's a simple enough formula. Bernoulli, so we can create a Bernoulli distribution object by calling towards the distributions of Bernoulli given the probs and get the Bernoulli dot probs. I can plot the PDF. So, the probability of the probability of heads, so P0 is, this should be P1. Probability of heads is no. Okay, so the labels, anyway, forget about the bar plot for now. It's just indicating that the probability of heads is, or success is 0.3, the probability of failure would be 0.7. Oh, which is correct, this case is correct, bar plot. So 0 is failure, 1 is success. One important thing to be very careful when we are using the Bernoulli distribution in various parameterizations is certain libraries use the default input method as the logits and not probabilities. So if we were to instead write Bernoulli dot equal to torch distributions or Bernoulli logits equal to 0.3, Bernoulli dot probs, it will get 0.57. Right. The benefits of using logits is that you are not restricted to 0 to 1 range. Right. You can think of the sigmoid function as sigma x equal to 1 over 1 plus e to the power minus x. The inverse of this function is known as the logits function. So this will give you something which is between minus infinity to infinity. Right. Again, you'll know more when you need to know more. This is a common bug where people don't understand the defaults, and sometimes when they want to pass probabilities, they end up accidentally passing the logits. We can get a sample from this distribution. It will be either a 0 or a 1. In this case, I have sampled 10 values. If I were to find the number of ones in this sample, what is it? 0, right? So that's happened because I recalculated this and I'm using the logits. But if I were to instead use the probs 0.3 and now get some 10 samples, they seem to be 4 ones, right? Which 5? 1, 2, 3, 4. 4 ones, which seems to be higher than what we'd expected. But if you take the 1000 samples and if we count the number of ones, they seem to be roughly 300, which is what we'd expected because the probability of heads for each sample was 0.3. Right? Now we go back to the slides and we are now going to try and estimate this parameter theta, which is the probability of heads. We're trying to obtain the maximum likelihood estimate for this parameter. Again, given a data set x1 through xn, we can find out the density, the likelihood function, which is a product of the individual PMFs, and we can also view this as a graphical model where start from theta we get xn, and we can find out the log likelihood function. Now again, I want you to take your notebooks, find out the log likelihood function and find the optima with respect to it, and find out the theta hat equal to the number of heads or the number of successes divided by the number of total draws. Can you do that in your notebook? Find out the estimate, the MLE for theta hat. Is everyone able to arrive at this expression of log likelihood, which is summation over the n examples xi log theta plus 1 minus xi log 1 minus theta. Here xi could be either 0 or 1. So once you have it, you need to just find out the derivative with respect to theta and set it to 0. Fortunately for us, the calculation is fairly easy. The analytical expression is fairly easy because the only two terms having theta are logarithmic terms. So what is the theta hat that we obtain? Sorry? Average? Yeah. So if we follow the procedure, we find the derivative with respect to theta, set it to 0. We'd obtain that the maximum likelihood estimate for theta is summation I equal to 1 to n of xi over n. Right? Xi is either 0 or 1. This is just the number of, this is the fraction of the examples where we have hits or success. Right? So as we saw that this estimate could be highly misleading, right? We saw this a few minutes back. Let me go back. Let's say I had 4 examples. So using this example, what would you estimate theta to be? You have 2 successes, so 2 over 4, 0.5. What is theta now? 0. The true value of theta is 0.3. If your sample sizes are very small, MLE will likely give you wrong results, right? But if the sample size is very large, then you would be able to get roughly fairly good estimates. This also relates to one of the questions in the assignment, that when you're trying to estimate certain quantities, we saw this today also, as you increase the sample size, what happens to your estimate? Does this estimate is also an unbiased estimate, by the way, right? So the true value you would be able to recover using our MLE, but there is the other notion of the variance in your estimator. And the variance on the estimator, you will be able to show that as you increase the size of the data, your variance will reduce, which is as expected, because you're trying to now estimate from a much larger data set. So we'll end today's lecture at this point. It was a bit of a mathematically heavy lecture, I'd say. We looked at the likelihood function in the case of normal distribution with values mu and sigma. We looked at the likelihood function, the log likelihood function, and we said that we can create such contour plots where our aim is to find out the mu and sigma, which will maximize the log likelihood. And we can now perhaps start with some values of mu and sigma and traverse around this optimization, through the optimization procedure, traverse around this surface and find out the optimal values of mu and sigma, which maximize this objective. The next thing which we discussed was we were trying to find out the MLE analytically for mu and sigma. The analytical MLE that we obtained for the 1D for the 1D distribution, normal distribution, is the empirical mean and the empirical standard deviation, or the empirical variance when we are estimating the variance. But we looked at some examples and found out that the empirical variance seems to be biased, which means that it's underestimation. It is underestimating the true value of the variance. So therefore, software libraries provide a correction factor known as Bessel's correction factor. And then we looked at certain examples to show and understand why, because we're looking at the samples, how we may end up underestimating the variance. How, as we increase the size of the data set, samples that we have, the problem becomes smaller. Any questions? Okay, thank you. We'll end this lecture. The next lecture again is in the new classroom, 7208, and new time 11:30 a.m. on Thursday. Meet you then.